So using problem 11 and the numbers on this particular test, we've got a Ferris wheel with a radius of 30 feet. It takes 4 minutes to make 6 revolutions. We want the angular speed in radians per minute and the linear speed in radians per minute. So to get the angular speed, I'm going to start with the number of revolutions per minute. I get 6 revolutions in 4 minutes, and then convert that to radians using the fact that 1 revolution consists of 2 pi radians. And so once I cancel revolutions, I've got radians per minute, and that gives me 12 pi divided by 4 radians per minute. 4 goes into 12 3 times, so the angular velocity is 3 pi radians per minute. Once you have that, the linear velocity is just the product of the radius with the angular velocity. And so if I take that 3 pi and multiply it by 30, a radian is also measured in feet here, and so we have 90 pi feet per minute. And then in number 12, a person gets on this Ferris wheel and turns. Person gets on. Excuse me. Person gets on right here at the bottom seat, and from this location turns a distance of 2 pi over 3 radians. So if I stretch this out and make that straight line, that's pi radians. If I go 2/3 of the way from there, there would be 1/3, there would be 2/3. So the person rotates to here, and the question is, how high is this length right here? So if I put this right angle here, I know this amount is the radius. So this part here is the 30 feet. This part is the y value in this right triangle. Now, this entire angle from here to here was 2 pi over 3. But halfway is pi over 2. So this angle in here would be the difference between the pi over 2 and the 2 pi over 3. So that angle theta is pi over 2, 2 pi over 3 minus pi over 2. If I get a common denominator of 6, I have 4 pi over 6 minus 3 pi over 6. So that interior angle in that right triangle is pi over 6. And I want to know this height here to give me that length right there. So for now, I'm going to call that y. I know that this hypotenuse is the same as the radius of the circle, so that's also 30. And let me pull that triangle out over here then. There's that pi over 6 angle. There's the y that I'm looking for, and this is 30. The person sitting in this Ferris wheel car right at this point is at a height of 30 plus y feet. So I'm going to go over here and get that y. In this right triangle, y is opposite the given angle, and I also have the hypotenuse. So if you remember your right triangle trigonometry, the sine of that angle will give me the opposite over the hypotenuse. So the sine of pi over 6 is y divided by 30. Quick, 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 what's the sine of pi over 6? I want the sine of it. 1/2. So this number on the left is 1/2. Now I'm going to solve for y by multiplying both sides by 30. So y is going to be 15. That means at that At that stopping point, this person is going to be 30 plus 15 feet high, 45 feet. So I made that into a 4-point bonus. I didn't think there was many steps to it, but I also didn't see many of you working at this. A lot of you were looking at this arc length, but we want the vertical length. So I hope that it referred you back to your right triangle trig. I don't want you to forget things just because it was on the first test. But that was a 4-point bonus, and then the last problem was a 6-point bonus. What else would you like to see? There was one I want to work the, I want to work number 6 and 7. Number 6 and 7 I want to work. Now you might have different numbers, so just bear with me. I'm just going to use the numbers that are on this test. On number 6, we've got the radius of a circle is 24 centimeters. And we want the length of an arc intercepted by a central angle of 3 pi over 4 radians. So that one uses the formula arc length is r times theta. So this one was a quickie. You just multiply the 3 pi over 4 with the 24. Four goes into 24 6 times. 6 times 3 is 18. So the arc length is 18 pi centimeters. And then on number 7, the other formula we had was for the area of a sector. Area is equal to theta divided by 2 times r squared. Many of you forgot the divided by 2 part. And in this one, we're told that the area is 50 pi over 3 square centimeters. And the radius is 5. Find theta. So essentially, it's just a matter of plugging those things into the formula and then being able to do the algebraic steps to get the theta out of there. So I'm going to put the 50 pi over 3 over here on the left. Theta we don't know. And r is 5. So when I do the squaring on the right-hand side, I get 25 over 2 times theta. And so to solve for theta, I just multiply both sides by the reciprocal. Multiply both sides by 2 over 25. And then the 25 goes into 50 twice. And so my angle is 4 pi over 3. But the catch here was that I want the angle in degrees. So next we convert this to degrees. We convert an angle from radian measure to degree measure by multiplying by 180 over pi. So I'm going to take 4 pi over 3 times 180 over pi. The pi's will cancel. 3 times 60 is 180. 4 times 60 is 240 degrees. Now I give multiple choice tests in order for things to be easy to grade when you have the right answer. When you don't have the right answer, I'd like to be able to give you some partial credit, but many of you are not putting any work down. And I don't know how you can get from area of a sector to here without writing anything down. I don't understand how that happens. maybe you're randomly circling things, that makes it pretty hard to give you partial credit. So please try to show some work. And I'll try to give you something if you write something correctly. If you're just circling things, it's hard to give partial credit, and that was a 5-point problem. So for me, I try to make the problems many with few points each. The next two I want to do are the two graphs at the end, where you had to come up with the formula for the graph. And so one of the graphs looked something like this. It had an intercept at pi, and then up here at 2, and then at 4 pi, it was back to 2. Oops. So 4 pi, it was back to 2, and at 2 pi, it was at 2. At 3 pi, it was at 3. Yep. And the graph in between, something like this. So I'll put this little connecting line here between the front point and the end point. They're supposed to be nice and symmetric. I don't know why I didn't make it that way. That should have been up here a bit higher. But the point is, it looks like a cycle like that. So that's an upside down sine curve. And oh, this was at 1. That's why it looks funny. This was labeled as a 1. So this point up here would be at 3. Okay, so it's an upside down sine curve. And from the intercept to the 0 on both sides is 1 unit. So that means the amplitude is going to be 1, but since it's upside down, we're going to make it -1. The period is 4 pi. Our period is normally 2 pi, so B is the scaling factor. I'm going to take that equation and solve it for B by multiplying by B and then divide by 4 pi. So that says B is going to be 1/2. There is no phase shift, so C is equal to 0. And the graph has been picked up. So that means, let's see, normally this 2 is at the 0 line. So the graph has been picked up 2 units. So I said this was a sine curve of the form f of x is equal to a sine bx plus c plus d. A was -1. B is 1/2. C is 0. D is 2. So minus sine of 1/2 x plus 2 is what I was looking for there. The other graph, get this drawn right. Oops, I guess I need to go down a little bit lower. The other graph at pi over 4 goes to 1/2. So this is 0.5, and this is marked as being at pi over 4. And then it crosses at pi over 2. And then at 3 pi over 4, it's down to -1/2. And then at 5 pi over 4, oops, sorry, at pi it crosses, and then out here is 5 pi over 4. So it crossed me at pi over 2, pi, and then back here it's up again. And so it was one cycle of a cosine curve that's right side up. So we're going to use f of x is equal to a cosine bx plus c plus d. The a is the amplitude, so from the intercept to the height is 0.5. The period is the difference between 5 pi over 4 and pi over 4. Which is 4 pi over 4, or pi. And as before, the ratio 2 pi over b is equal to the period. We solve that for b. So if I multiply both sides for b, I get 2 pi is equal to b pi, so b has to be 2. Okay, so I get a is 0.05, b is 2. There is a phase shift because normally our sine and cosine curves start at 0. This one starts at pi over 4. So this has been moved pi over 4 to the right. And the ratio minus c over b gives us that phase shift. We found b to be 2. So when I solve this for c, I'll multiply by 2 and by a negative sign. So c is negative 2 pi over 4, which says c is a negative pi over 2. There's no shift up or down, so d is 0. And now if I plug it all in there, I get that f of x is 0.5 cosine 2x minus pi over 2 plus 0. Okay. Again, I thought this took some work, some writing on paper. And some of you just plopped down equations, and I thought, okay, can't give partial credit. I don't see what your thought process is. So try to write more, try to communicate more what you're doing. Anything else? All right, let's tuck this away then. Next test I said was sometime in November, November 19th. Look at all these papers. What am I gonna do with these? Who's got the match? One thing I absolutely need everybody to do is check Blackboard and make sure your score is accurately recorded. It's so easy to make typing mistakes, or my cat walks across the keyboard and clears all your grades or something like that. So make sure your grade is entered in Blackboard the way it's supposed to be. If not, please let me know. Take a photograph of your test and send it to me, and I'll put it in there correctly. And you guys at home, please come by sometime and get your test before I fire that bad boy up. Has anybody been working on web work? Do you have any questions about anything going on web work? Yes, ma'am. Number 12, would you happen to know what it looks like? No? All right, let me try to get web work number 12 up here. So while I'm pulling up web work, I want you to write down the 3 forms of the Pythagorean identity. The one that relates sines and cosines, the one that relates tangents with secants, and the one that relates cotangents with cosecants. I want you to have those looking at you. So on your notebook paper, write me all of them down, beginning with sine squared plus cosine squared is 1. Let me see if I can find my web work. What are my Zoom people seeing? Did they see the screen or did they see that other screen? They're seeing that, huh? All right, let's write these down. I've got tangent cubed minus secant squared times tangent. Is divided by a cotangent of minus x. And we want to know what that equals. I'll leave some space there. The next one is cosecant to the fourth minus the cotangent to the fourth. And then the third part is 1 over sine cubed that's pleasant, minus the cotangent squared of x over sine of x. All right, let's get back to my. We're going to work on. You want problem 9 from the test, or did you want problem 9 from web work? I guess that's problem 9 from web work. Okay, I'll do that one as well. Let me put that at the bottom. Secant of x minus 1 times secant of x plus 1. So I'll do it on the next page. Okay, let me move that down. I'll get that. Okay, so I asked you to write the 3 Pythagorean identities, and here they are. Sine squared of x plus cosine squared of x is equal to 1. Then if you divide all of that by cosine squared, the next identity would look like the tangent squared of x plus 1 is secant squared of x. Or if I divided everything here by sine squared, I get 1 plus cotangent squared is equal to the cosecant squared. So I think we're going to need to use that on the first problem. I also see a negative x inside here, so we need to use our even and odd properties. Let's see, there are 2 even functions, and that's the cosine and the secant, where the cosine of the opposite of x gives you the exact same thing as the cosine of the positive x. 1 over the cosine is the secant, so it does the same. Sine is an odd function that says the sine of minus x is minus the sine of x. The only 2 even functions are the ones that deal entirely with cosine, cosine and 1 over cosine. All the rest of them have a sign in them. So all of the other trig functions are odd. That means down here where I have the cotangent of minus x, I can just replace that with the cotangent of x, but put a minus sign in front of it. Can do that with every trig function except cosine and secant. With cosine and secant, I would just replace it with the trig function of the positive angle. Then on top, I have 2 terms separated by the minus sign, and these 2 terms have a common factor of the tangent of x. So I'm going to factor it out and put it right here. And now work backwards. I'm going to put in the parentheses what I would multiply by the tangent of x to get the tangent cubed. So it looks like I'm going to need a tangent squared. Then I've got the minus sign. I've taken this tangent out, so what I have left is secant squared. I used one identity and I factored. And now let's look above. If I take this identity here and rearrange it so that I have a tangent squared minus a secant squared by subtracting secant squared from both sides, then I would have to move this one over and I would get tangent squared minus secant squared is equal to -1. Does everybody see how that happens? Tangent squared minus secant squared is -1. So I'm going to replace that with -1 in there. That means these minus signs cancel. So now I've got a positive ratio, tangent of x over cotangent of x. But tangent is sine over cosine. Cotangent is cosine over sine. And to divide one fraction by another, one just takes the fraction in the denominator, flips it over, and multiplies. So now the sine of x is on top, and the cosine of x is on the bottom. And so when I multiply straight across, I get the sine squared of x. And on the bottom, I get cosine squared of x. I think if you entered that in WebWork, it would take it. Or you can use the fact that sine over cosine is tangent. So sine squared over cosine squared is tangent squared. Believe any of that? Okay, the next one. I don't know what you notice when you see this, but when I look at something like the difference and even powers, I think of the difference of squares formula. I think of a squared minus b squared is a minus b times a plus b. I know I've got fourth powers, but I can think of this as a cosecant squared that's squared. And I can think of this as a cotangent squared that's squared. So my a is cosecant squared and my b is cotangent squared. And now I'm going to use that. This should factor into a minus b, cosecant squared of x minus cotangent squared of x, times a plus b. Now I'm going to look up and check out the trig identity that involves cosecants and cotangents, this one here. If I subtract cotangent squared from both sides, it tells me that cosecant squared minus cotangent squared is equal to 1. Cosecant squared minus cotangent squared is equal to 1. Now I'm going to write this expression on the right-hand side in terms of sines and cosines. Cosecant squared is 1 over sine squared. Cotangent squared is cosine squared over sine squared. And I can now put that as a single fraction that looks like 1 plus the cosine squared of x over sine squared of x. I don't know which one looks better. I don't know if WebWork will take this one or that one, but I think they're both good. Try either one of them and see. The third one involves subtracting two fractions. And I can only subtract fractions if they have a common denominator. So let's see, what I'm going to do to get that common denominator is replace that cotangent squared with cosine squared over sine squared. Let's replace cotangent squared with cosine squared over sine squared. Then I've got this fraction divided by this one. So we'll do that flip and multiply thing. Let's copy down this first term again. 1 over the sine cubed of x minus, now I'm going to copy the numerator down, cosine squared of x over sine squared of x. Flip that over and it becomes multiplied by 1 over the sine of x. And so that's going to give me the sine cubed. So I have 1 over sine cubed of x minus the cosine squared over the sine cubed of x. And now I have a common denominator, so I can make that into a single fraction. And so I can make it look like 1 minus cosine squared of x all over sine cubed of x. But wait, sine squared plus cosine squared is 1. So if I want 1 minus cosine squared, I'd subtract cosine squared. And what's left over here is sine squared. So 1 minus cosine squared can be replaced by sine squared. So I have sine squared of x divided by sine cubed of x. Those cancel. 2 from upstairs and 2 from downstairs leaves me with 1 over sine of x. Which trig function is 1 over sine of x? So you can enter the cosecant of x, I believe, as the answer to this one. Okay? So you just kind of play with them, replace them and get them sines and cosines, subtract, divide, factor, cancel. Do all the little algebra things you can until you get something that looks a little bit prettier. So next I work number 9. We're supposed to simplify this, that. Bigger table here. There we go. Secant of x minus 1 times the secant of x plus 1. Now our trig identities have squares in them. So I'm going to multiply this out and see if I get anything. I'm going to take the first 2 and multiply them together. Secant times secant will give me a secant squared. Then the first one times the last one gives me plus the secant of x. Now I'm going to use the minus 1. Minus 1 times secant gives me minus the secant of x. And then finally, minus 1 times positive 1 gives me a minus 1. And those two secants inside do add each other out. So I'm left with secant squared of x minus 1. So I'm going to go back to my page that have my Pythagorean identities on them. If secant squared is tangent squared plus 1, then secant squared minus 1 is just tangent squared. And I think we're done here. Okay. So not only does it help if you know the 3 Pythagorean identities, know them in all different permutations, whether you move things over left, right, or not. Okay. Anything else web workish? I've got one here. Sine of x plus cosine squared of x divided by sine of x. If you enter those answers, which answers? For number 12. Yeah, you can, there's many ways you can do these. You can go from cotangent to 1 over tangent. So I need to go back at number 12 and it says something's not being taken here. Oh, golly. Let me see. Back to number 12. Which one's not being taken? None of them? What I get is my answer here. Let me see what I said. I said that that one was equal to tangent squared of x. Well, it says at least one. Let me get them all entered first. What I say was the second one. I think I said that was so this one was 1 plus the cosine squared of x divided by sine squared of x. And then this last one I said was cosecant of x. Now let me submit them. I got them all right. Booyah. So maybe a typing error, make sure you get your entire numerator in parentheses. Make sure you include the article of the trig function. You can't just put the abbreviation of the trig function and leave out the of x. So just be careful when you type these things in. All right, so I had another one somewhere. Let's see what my chat was. I want cosine of x isn't all mine did. Mine took it. Mine took the answers. You saw green, didn't you? Try it again. Just be careful with your typing. Okay, sine of x plus the cosine squared of x divided by the sine of x. Now, I'm not sure if that sine of x is only under the cosine squared or if it's under all of that. But let me check. Let's see which one that might be. Not there. Let's see it there. Under the cosine of x only. Okay, so let me try this. Sine of x plus the cosine squared of x divided by sine of x. Okay, so here I go. I've got 2 fractions to add. I'm going to add them by getting a common denominator. First fraction already has, the first fraction has a 1, the second fraction has a sign. So the common denominator is going to be the sine of x, which means I have to take this first fraction here and multiply by 1 in the form of the sine of x over the sine of x. And now that I have the sine of x underneath both of them, I'm going to make them into one fraction. And the first fraction contributes a sine squared of x, and the second fraction a cosine squared of x. And there's my favorite sum, sine squared plus cosine squared. What does that equal? That's a 1. So I get this to 1 over the sine of x, and that's another trig function. Which trig function is 1 over sine of x? That is the cosecant of x. Okay? So if you're having trouble entering these in WebWork and getting the right answer, just click on the email the instructor. That way I can see what you've entered and see if it's a parentheses problem or something like that. Anything else? Anything else WebWorkish? Real people? Television screen people? We're good? I bet you said, you know, those identities are fun, but I wish I had a few more. It goes this way. I got a boatload of identities for you, but I got to show you why we have a need for them. What do you get when you add, say, pi 6 with pi 6 plus pi thirds? What is pi 6 plus pi thirds? Quickly add those together. Pi 6 plus pi thirds. Pi 6 plus pi thirds is pi 6 plus 2 pi 6, which is 3 pi 6, or pi halves, correct? All right, so I want to show you something called an addition formula for sines and cosines. So first, we're gonna, and this is in section, chapter, what chapter are we even in? 5? Section 5.3 and 5.4, we're going to get addition formulas and subtraction formulas for our trig functions. And here's why we need them. Note that in general, the cosine of A plus B is not equal to the cosine of A plus the cosine of B. You cannot distribute a trig function through parentheses. And I'm going to use my pi 6 plus pi thirds example. Look at the cosine of pi 6 plus pi thirds. By doing the arithmetic, that should be equivalent to the cosine of pi halves. Does anybody in this room know the value of the cosine of pi halves? The value of the cosine at pi halves? 0. Now I'm going to take the cosine of pi 6 and add it to the cosine of pi thirds individually, and we ain't going to get 0. Cosine of pi over 6 plus the cosine of pi over 3. All right, what is the cosine of pi over 6? Square root of 3 over 2. And what is the cosine of pi thirds? And where I come from, the square root of 3 over 2 plus a half is not 0. So if you add the angles, then apply the trig function, you get 0. If you take the individual trig function of the angles being added, you don't get 0. So there is not a distributive property for these things. It's going to look very strange to you what the actual addition formula is, but I'm going to show it to you with this picture here. Yeah, I didn't think I could draw this picture as pretty. Start by drawing the unit circle. That's the circle, x squared plus y squared is equal to 1. So draw the circle that intersects the x and y axes at 1, 0, 0, 1, negative 1, 0. Once you have that circle drawn, let's construct angle A to be an acute angle. I'll do it in red here. Angle A is an acute angle that intercepts that circle at the point I've labeled P2. Remember that on the unit circle, the x coordinate is the cosine of that angle, and the y coordinate is the sine of that angle. So the ordered pair contributed to point P2 is cosine A, sine A. The next thing I want you to do is arbitrarily form an angle of measure B from that ray, 0, P2. Form that angle B to intercept the circle in quadrant 2 at a point P1. So if I piece these two angles together, the red one and the blue one, I get this big angle right here that I'm going to highlight in yellow as the sum of those two angles, which means the coordinates at the point I've labeled P1 is the cosine of A plus B is the x coordinate, and the sine of A plus B is the y coordinate. Then the next ray, I want you to put whatever size this angle is, draw an angle in standard position of that same size, but going in the negative direction. Construct angle minus B so that it is now in the fourth quadrant, so that this angle right here, B, and minus B have the same magnitude. And that's going to intersect the unit circle at point number 4, which has as its ordered pair the cosine of minus B and the sine of minus B. But the cosine is an even function, which says the cosine of minus B is the same as the cosine of B. Sine is an odd function, so the sine of minus B is minus the sine of B. Now the dotted line connects point 1 to the intercept on the x-axis 1, 0. That length of the line can be found using the distance formula. Anybody in here remember how to find the distance between 2 points? Does anybody know that, say, the distance between the ordered pair x1, y1 and x2, y2 looks like the Pythagorean theorem? X2 minus x1 squared plus y2 minus y1 squared. Does that look familiar to anybody? Going back to the circle now, this distance, P1 to P3, was formed with angle A plus B. Since angle minus B had the same magnitude of angle B, just wrapped in the other direction, the distance between P2 and P4 is also equal. So P2, P4 has the same length as P1, P3. So I'm going to write that here. P1, P3 has the same distance as P2, P4. Back up a bit. You can see the circles. One more time back. Hey, I said back. Now I'm going to use the distance formula. I'm going to take these two x's and subtract them and square them. So for P1, P3, I'm going to have the cosine of A plus B minus 1 squared. Now I'm going to subtract the x's, but this x is just a 0. So the next term I'm adding to it is the sine of A plus B. And that'll be squared. So I'm going to put the square right here. It's got the square root sign on it. Now the distance between P2 and P4. The difference in the x's is cosine of A minus the cosine of B. Then I got to square that. And then the difference in the y's is sine of A minus a minus sine of B. So that's a distance formula acting on both of those. Drawing that radical sign is getting to be a pain in the neck, and I've only drawn it once. So I'm going to get rid of it by squaring both sides. So in the next step, I'm not going to write the radical sign. But I am going to square this, I'm going to square that, and I'm going to square that. But I want you to think of this one is the sine of A plus the sine of B that's being squared. So when I square this using cosine of A plus B minus 1 times itself, I'm going to get the first term squared. 2 times the product of this. Well, that product gives you minus cosine of A plus B. So I'm going to get 2 of those. Minus 2 cosine of A plus B plus the last term squared. So that gives me plus 1. And then I have sine squared of A plus B. And this is a plus right here, sorry. Now I'm going to go across to the other side, and I'm going to do the squaring over there. Cosine of A minus the cosine of B squared will give me cosine squared of A, twice the product, so minus 2 cosine of A, cosine of B, plus the last term squared to be cosine squared of B. And now I'm going to square this, and I'm going to get something very similar. I'm going to get a sine squared of A, twice the product, so twice sine A cosine A, plus the sine of B squared. So this is all one side right here. All right, let's go to the left-hand side. I'm going to add this with this. Cosine squared of A plus B plus sine squared of A plus B. What do I get? Cosine squared plus sine squared at the same angle. That's 1, right? So that what I've underlined in yellow is 1. I'm going to add that 1 to that 1 and get 2. Now let me see if there's anything on the right-hand side I can add. This should say plus the sine squared of B. I've got 1 right here. I've got another 1 right here. So that's 2. And then I have all of this, minus 2 cosine A cosine B, plus 2 sine A cosine A. Where did that come from? I wanted one of those to be a B. Ah, did I square something wrong? Sine squared of A, that should be a sine of B right here. Talking and writing is getting too hard. 2 times this inner product, so I should have a sine of B right here. So that's what's left over here with that 2. I need to move this down a little bit. Let me just copy it down here so it doesn't draw into itself. All right, so over here I had the two yellows that I circled. Then I have minus 2 cosine A, cosine B, plus 2 sine A, sine B. I can subtract this 2 from both sides, and that's gone. Then everything here has a 2 in it. I'm going to divide everything by negative 2. And here's my addition formula. It says the cosine of A plus B is equal to the cosine of A times the cosine of B. This will leave me a minus sine of A, sine of B. There's your first of your addition formulas. The cosine of A plus B is not as easy as taking the cosine of A and adding to it the cosine of B. Trig functions are fickle that way. They're non-algebraic functions. Cosine of A plus B is equal to cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. And I'm going to convince you that this is true by using my A and B that I used in our initial example, pi 6 plus pi thirds. So that was just the derivation. That was for entertainment purposes. I can see that you're overjoyed in having had to sit through that, and you can't get those 5 minutes of your life back. I'm not going to make you do that kind of thing. I want you to be able to use this formula. I'm not even going to make you memorize this formula. I just want you to know how to use it. So let me show you that it is indeed true, because a lot of you think I'm lying to you. Not at this instant. So let me show you that it works. In our last example, we had the cosine of pi 6 plus pi thirds, and we got 0 out of that. Well, I'm going to use this goofy ass formula where A is pi 6 and B is pi thirds, spread it out, and this right-hand side is actually going to add up to 0. So I'm going to verify that the cosine of A plus B is cosine A, cosine B minus sine A, sine B by letting A be pi over 6 and B be pi over 3. So earlier, we said that the cosine of pi over 6 plus pi over 3 is the same as the cosine of pi halves by brute force adding pi 6 to pi thirds is 0. Now I'm going to fill those numbers into the right-hand side. Compare that to the cosine of A. Well, A is going to be pi over 6. Cosine of B, B is pi over 3, minus the sine of pi over 6, sine of pi over 3. Cosine of pi 6 is square root of 3 over 2. Sine of pi 6 is a half. Cosine of pi thirds is a half. Sine of pi thirds is square root of 3 over 2. Sine of pi 6 is a half. Sine of pi thirds is square root of 3 over 2. Looky there, I got square root of 3 over 4 minus the square root of 3 over 4 is equal to 0. So, yep, it works. Yep, it works. And from that formula, we can get a difference formula. So go back to this formula right here. So start with cosine of A plus B is cosine A cosine B minus sine A sine B. Let's replace every B with minus B so that I get a subtraction formula. Then I have the cosine of A plus minus B is cosine A, cosine of minus B, minus sine of A, sine of minus B. I'm going to rewrite that as the cosine of A minus B. And remember that cosine is even. Cosine of minus B is the same as the cosine of B. Sine is odd, so sine of minus B is minus sine of B. Anybody repeat what I just said? Charlie Brown's teacher. Wah, 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 wah. Cosine of minus B is the cosine of B. Sine of minus B is minus sine of B. So I put these two negatives together and it gives me a plus inside. Cosine A, cosine B, plus sine A, sine B. That's the difference formula. It looks just like the sum formula, but it's got a different operation in between the two terms. It's got a plus where that has a minus. And then up here for this one, where I have a plus on one side, I have a minus on the other, but the pairing is the same. To get the version of the sine formulas, we'll just use the fact that sine and cosine differ by 90 degrees. They have the same value, but they're cofunctions. Cosine of A is the same as the sine of 90 minus A. And the sine of A is the same as the cosine of 90 minus A. So the sine of A is the same as the cosine of 90 minus A, and vice versa. Sine of 90 minus A is the cosine of A. If I went in all of these things here and did a manipulation like that, you're going to have to believe me. Here's just a lightning bolt. It just comes as a gift from the sky. I'm going to just give you the two. That's a good looking lightning bolt. I'm going to give you the two formulas for sine. That the sine of A minus B looks like sine A cosine B minus cosine A sine B. Whereas the cosine difference formula had a pair of cosines and a pair of sines, the sine has them paired up in that way with the same sign SIGN in between, so that the sine of A plus B looks just like that, but with a plus sign here. I'm pretty amazed that I remembered that identity myself. Maybe it's right. So we have 4 identities, and I'm going to work examples with them next time. We have the sine of A plus B, the cosine of A plus B, sine of A minus B, cosine of A minus B. I'll work examples with them next time, and then we're going to go from there to get double angle formulas. Guess how we get the tangent of A plus B formula? Divide the sine of A plus B by the cosine of A plus B, right?
Should have guessed that.
All right, have a marvelous day. Your brain is fried, so is mine. You just had to sit there. Yes, sir. I marked it wrong. Okay, let me get this off of here so we don't divulge any of your private information. Stop share. Stop.